In this next example concerning mathematical induction, I thought we could prove an inequality. We can try to prove that 2 to the n is greater than n squared whenever n is greater than or equal to 5. So here our base case will be n equals 5. So let's check the base case. Base case, n equals 5. So the left-hand side, that'll get us, well, 2 to the 5, which I think is 32. 2, 4, 8, 16, 32. Yeah, that seems reasonable. Okay, and this is indeed greater than 5 squared, which is 25, which is the right-hand side. So the base case holds. So now we need to do the induction step. And as always, we need to make an induction hypothesis. Okay, so what do? We suppose that 2 to the n is greater than n squared for all n, and now we allow n to go from 5, because that's the base case, up until some fixed capital N, where this capital N is greater than or equal to 5. Okay, so that's our assumption. Next, we consider 2 to the capital N plus 1. So this is nothing more than 2 times 2 to the n, which is 2 to the n plus 2 to the n. Now we can use our induction hypothesis. So by the induction hypothesis, we know each of these 2 to the n's are greater than n squared each. Now we need another inequality here to progress. So I think maybe what would be easier is to observe if I have n minus 1 and I were to square it, then because n must be greater than or equal to 5, this thing must be greater than or equal to 4 squared, which is 16, of course. And clearly this is bigger than 2. Now, you might wonder why I've done this. Well, if we have a look at this and expand the left-hand side, we end up with n squared minus 2n plus 1 is strictly larger than 2. And so this means that n squared will be greater than 2n plus 1. So if we go back to this term, and let's put it down here maybe. So we have n squared plus n squared. It's greater than, well, let's just leave one of the n squareds and write 2n plus 1, because this thing is smaller than this by this inequality up here. Okay, and we can factorize this side and get n plus 1 all squared. So what have we shown? We've shown that 2 to the n plus 1 is indeed greater than n plus 1 squared. Okay, so this completes our induction. So what we've proved is that indeed 2 to the power of n is strictly greater than n squared whenever n is greater than or equal to 5.